Why is my screen blank? There we go. Okay. I don't know if that was weird for you, but it was weird for me. So here we go. So last time we started 2-3 and we were talking about this essentially interpreting the derivative. So we kind of went over 2 ways to do that. You kind of have the rate way or the step way. Is this super laggy or did I do something stupid? What? This isn't good. Oh, no. Can anyone see anything? Because I can't. So I assume y'all can't. There it goes. Okay, now I can see things. All right, well, I'm gonna try my best to keep up then, because my screen's obviously not being right. Anyway, we went over ways to interpret a derivative. So we kind of went over the rate way and the step way. At this point, I'm kind of going to jump between kind of both of them. Sometimes I'm going to pick one over the other because I know the direction I want to go with it. So we had kind of one more idea to talk about down here. Is it just like my screen that's just not having a fun time? There it goes. That's not fun. Anyway, it's not letting you in or showing a call. Teams is apparently being very buggy today. All right, so if we try this guy, so we've got fertilizers can improve agricultural production. A Cornell University study on maize, which is just corn production in Kenya, found that the average value is going to be given by y equals f of x in Kenyan shillings of the yearly maize production from an average plot of land is a function of the quantity of fertilizer used in kilograms. So essentially we have our x value is going to be the quantity of fertilizer in kilograms, and then we're going to have essentially our y value is going to be the amount of Kenyan shillings, and that's just their currency. So the first thing we want to do is we want to interpret the 2 statements f of 5 equals 11,500 and then f prime of 5 equals 350. So the first one isn't a derivative value at all, it's just a regular old value. So we just want to say, well, 5 is an x value, so that's going to be the amount of kilograms of fertilizer. And then our 11,500 is going to be that Kenyan shillings amount. So we could say something like, if 5 kilograms of fertilizer is used, the average value for maize production. Wow, what happened there? Is that 11,500 Kenyan shillings. a second, please. Okay. So that would be interpreting kind of our regular function piece, if you will. And now if I want to interpret the derivative, well, that's where we kind of have our choice of our right way or our step way. Because I know what I want to do with this next, I'm going to go with kind of that step way. So remember, that idea is essentially we start with 5 kilograms of fertilizer, and we're going to say if we increase that value by 1. So essentially I could say, now usually you would want to start with saying something about the 5 kilograms, but since I already have a previous sentence that calls on that 5 kilograms, I'm just going to kind of start with the adding the 1 extra. So essentially, if 1 more kilogram of fertilizer is used, we're essentially saying add 1 to the x value. Let screen catch up. Maybe both of my screens are frozen in different places. That's amazing. Hello. Yeah. Okay, so we started at the 5 kilograms in the previous sentence. If we add on 1 more kilogram of fertilizer, then essentially we'll then say that the y value, that Kenyan shillings amount, is going to increase by the derivative value. So then the average value increases by 350 Kenyan shillings. If you wanted to go the right way, you would have to say something like, after using 5 kilograms of fertilizer, the average value is increasing at a rate of 350 Kenyan shillings per kilogram. But again, I kind of wanted to specifically use this interpretation because of the next thing we want to do with it. So if I look at the next point, it says use statements in part A to estimate f of 6 and f of 10. So f of 6, well, that would be adding on an extra kilogram from f of 5. So if we think about what the derivative is telling us, what that slope is, and that's why I wrote it in that way, is that the slope of that derivative value, that slope, is telling us essentially how we're increasing if we add on 1 extra kilogram of fertilizer, which would get us to f of 6. So we can essentially estimate, we don't know it's perfectly that, we can estimate, if it'll catch up with me. Hello. And now I don't know if it's just my screen or everyone's screen. There we go. So we can estimate f of 6 by essentially starting with f of 5 and adding on the derivative value. Because that derivative value tells us if you increase the x by 1, how much you increase the y's by. Here we go. So we have the 11,500 plus 350 equals 11,850. So essentially we took the value we knew and we used kind of that derivative value to help us estimate the next value up. Now we don't know that that's the exact value of it. That's the best we can do though, is that we can estimate it kind of using that idea. Now what if I wanted to estimate f of 10? Well, first off, you don't want to use the estimations you just found. Like if you ever do some of these and you find some estimations, do not use the estimations you just found. But we can still use this f of 5 and f prime of 5. It's just going to get a little more wishy-washy. So if we think about it, if we have to start at 5, so if I want to start essentially trying to estimate f of 10, and I know that I have to start with f of 5 because that's the only value that I'm given originally. Well, if that derivative value is telling me, you know, if I increase by 1 in the x direction, well, if I want to get up to f of 10, well, then I didn't increase by 1, I increased by 5. So what I essentially need to do is I need to take that derivative value and multiply it by 5. And once again, my two screens are frozen in different spots. There we go. So instead of just adding one derivative value, we essentially have to add it 5 times because we want to take 5 steps, essentially up from 5. So if we were to calculate that, we'd get the 11,500 plus 5 times 350, which would give you 13,250. Both of these in Kenyan shillings if you like to keep track of units. Kenyan, why not actually? Kenyan shillings, once you catches up to me. If it's lagging for you like it's lagging for me. Teaching online is so much fun. One screen's good, the other screen's not. Questions, concerns on that idea? Well, I hope that it's all caught up for you guys, even though my one screen is still present. So essentially what we're going to be able to do here, and feel free to still type your questions if you have one, is that we're going to be able to use this derivative value to essentially estimate different values of the function. You can also go backwards. So say we wanted f of 4, instead of adding on a derivative value, would just subtract a derivative value. So we can kind of do this for no matter what value you want. You do want to be careful though, because if we think about it, which one of these two estimates would seem more reliable? Let me try to just reshare my screen again. You just made me do this every once in a while. Oh, that screen is really frozen. That one's having a fun time. So if we want to know which one of the two is more reliable, well, that would be f of 6. Usually I would have y'all think about it and tell me the answer, but doing that all on the internet doesn't go over well. So it would be f of 6 specifically because 6 is closer to 5. Ooh, the lag is real today. There we go. So essentially, the farther we get away from 5, the original value we had to look at, the worse the approximation is going to be. Because if you think about what functions can do, well, if a function, say my function looks something like, I don't know, like this, where this was 5 and this was 6, and all the way over here is 10. Well, essentially what I'm doing here, since I'm using a derivative value, I'm kind of using that slope of that tangent line. Once this catches up to me. Come on, I need a picture here. Thank you. So essentially, if we're looking at this derivative value, we're looking at that slope of the tangent line. So if my function were to look something like this, going over one space to 6 is perfectly fine. It's not perfect. But say the function does something super weird and starts going down really, really quickly, and then f of 10 ends up down here, but my f of 10 estimation for the thing essentially the process we just used would end me up all the way up there. Once it catches up, there we go. So we need to be really careful with these estimates, is we can estimate any value we want, but we also need to recognize that the farther we go, the worse it's going to get because we don't know exactly what the function is doing. So we need to be really careful there. So I'll leave that drawing in there, I guess. So part B that we just did, the one where we were finding f of 6 and f of 10, we used that derivative value to estimate values past 5. This is going to be something called tangent line approximation. Tangent line approximation. Sometimes it's also referred to as local linearity. You will hear me say tangent line approximation before you will ever hear me say local linearity, but in case you see the words local linearity anywhere. So essentially, if I were to write this out in generality, what we would have is we would have some f of x. Come on, there you go. We essentially start, so we always have to start with a value that we're given. So we're going to be given some f of a, and then we have to know the derivative value there, and we're essentially going to take that derivative value and multiply it by our change in x. And that's why we can find whatever value we want, forwards or backwards, because we just essentially take the difference between the, now we should be careful here, I should be careful here. This one is essentially, how do I want to write this? Let me write want minus have minus, looks like it's connected to the t. So like in the ones above, we had 6 and 10, so we would take 6 minus 5 and 10 minus 5, and that's what got us to the essentially 1 occurrence of the derivative value versus the 5 occurrences. But say you wanted f of 4, well then what you want is 4 and what you had was 5, so 4 minus 5 would be -1, which is why you would have to then subtract. So be careful there if you're trying to use the general form of it. Otherwise, just think about it, what is the difference between the number you have and the number you want? Do you have to go backwards to get there? Do you have to go forwards? If you have to go backwards, you're going to have to subtract values. If you want to go forward, you're going to have to add values, depending on the derivative value, because the derivative value could be negative. I should be careful there also. So this type of idea is also what gives us the tangent line. So we've talked about the tangent line a little bit. But what we're going to do now is we're actually going to find the equation of it. So essentially, what we were doing above is we were using that tangent line to approximate any value for the function. And remember, the farther you go out from the starting point, the less accurate the estimation is going to be. Because your tangent line might start going in one direction and your function might turn around and go in a completely opposite direction. So the farther out we are, the worse that approximation is going to be. So I'll leave that up for a few more seconds for people to get that down and catch up. And then we will find the equation of a tangent line. Well, we have another definition first. Whoops. But this next definition is something we've actually kind of already talked about. This is when your book formally defines them. So if we have 2 points in a function and draw a line between them, we have a secant line and a line that touches the graph of a function at exactly 1 point in a small interval we already know is the tangent line, because I've talked about it a bunch already. Once it catches up to me. So just to remind us, let me just draw an option of each. So if I have a tangent line here, and then say I just pick 2 points on the function, draw the line between them, and I've got a secant. So again, we've already kind of talked about those, but this is when your book formally defines it. I'll leave that up for a few more seconds before we go on to the example of finding the equation of the tangent line. And then we'll be done with 2.3, and we'll head over to 2.4. All right. So let's look at the process for finding the equation of the tangent line. Now, the way I'm going to write this process, once it catches up to me, is in such a way that it might sound weird at this point in time, but potentially by the end of this week, but definitely next week, we're going to be getting into derivative rules, which are going to also be used to find equations of tangent lines a lot. So essentially what I'm doing is I'm writing out this process here right now with kind of the fact that we'll have more tools later. So it might sound a bit odd, some of the phrasing for the tools we have right now, but once we get those extra tools, this process will still hold as well. If that made any sense. If not, don't worry about it. Anyway, so the first thing we're going to do is we're going to find the derivative. In parentheses, I'll put value. And that's kind of what I mean is right now we can only find derivative values, but next week we'll be able to find full just straight derivatives. So you can kind of come back to this process afterwards as well and still be able to use it. What we're going to do is we're going to plug in a to the original function. We're assuming that that's the point that we want to take the tangent line at. So we're going to plug it into the original function. Because if you think about it, we want to write the equation of a line. And if you think back to section 1.2, to write the equation of a line, we need two things. We need a point and a slope. So plugging that value into the original function is going to give us our point. And then in general, we're going to also plug it into the derivative. Or we'll just use the value if we found it separately. And that's going to give us our slope. So we essentially need two things, a point and a slope, and we use our original function and our derivative to find them. And then we're going to just use that linear equation process from chapter 1 to write the y equals mx plus b. So, about 5 more seconds before I go on to the example. I didn't finish answering this in my notes, so I don't know what the answer is. So I'll leave my calculator. So find the equation of the tangent line to x squared at x equals 5. So we're going to take x equals 5, and the first thing we're going to do is we're going to find the derivative value with it. So here we don't have the actual full derivative, but we can estimate f prime of 5. And so remember, at this point in time, to do that, we're going to have to use essentially that idea of estimating using the average rate of change. So this is where we use 5 and something really, really close to 5 once it catches up to me. And we find the average rate of change between the two. So essentially what I want to calculate is something like f of 5.001 minus f of 5 over 5.001 minus 5. So if I plug those into the function, I take 5.001 and I square it. And I type the right thing in my calculator. And then we take a bunch of decimal places. We get 25.010001 minus 25 divided by 0.001. So we get 10.001. And if any of you know derivative rules, you might be screaming at me to just take it to be 10. I'm not gonna. We're going to leave it as 10.001. So that's going to be our slope. This is going to end up being the slope of our tangent line. And now I need to find the point that I need to be able to write the equation of the line, because those are the two things I need. So we also need to find f of 5. So just plug that into the function, you get 25. So the point we're going to use is 525. So this derivative part is going to get easier next week, but at this point in time, this is how we have to do it. Well, maybe I shouldn't say easier, but we'll have a different, hopefully easier, hopefully quicker, depending on, anyway, I'm going to show. So we've got our slope and we've got our point, so now we want to write our equation y equals mx plus b. Well, we need to solve for b before we can write the actual answer, but we take these points, these numbers that I'm writing in backwards. So y was 25, slope was 10.001.
Just the slope or whatever. Well, you don't need to, like, just get whatever's there, like, not the salad.
There we go. All right, so we plugged those in. We've got 5 times 10.001. It's going to give us 50.005. So yes, it would have been nice if I just took it to be 10, but I didn't. So there. Subtract 50.005 from both sides. You get that B is negative 25.005. So the equation of the tangent line that we want is 10.001x minus 25.005. Once it catches up to me. So that's how we find the equation of a tangent line. You need to find your derivative value by doing our average rate of change estimation. Find the point you actually want to use by just plugging the point you care about into the function, and then use those to solve for B. Write your equation. Questions, concerns about that before we head over to 2.4? So in terms of your homework, I'm pretty sure it was just the last 3 questions that you couldn't answer before today. So it shouldn't be that hard to, if you were tracking along the way, to just get those last 3 done. Or if you're just the type of person who just gets it all done today, then it didn't matter anyway. Questions, concerns before we move on? Looks like no. Okie dokie. So we're on to 2.4, which is pretty short. I don't think we'll finish it today, but it's a pretty short chapter section. And it's also something we're kind of revisiting in a way, because your book does weird things and presents it really, really soon when that's weird. But anyway. So section 2.4 is called the second derivative. So since the derivative is itself a function, which we found out in 2.2, remember that one where I had the Desmos and it was super awkward because I had to jump between a bunch of things 5 million times and then we graphed that little lame parabola dude? So since we have that the derivative is a function itself, we defined the derivative function in that section. We can also calculate its derivative. So essentially you can calculate a derivative value of a derivative. So if y equals x, what we call the second derivative would be written as f double prime of x, is how you would read that. Or in Leibniz notation, which we talked about in 2.3. So remember, regular Leibniz notation was dy over dx. Once it catches up to me. So just side note reminder, hello. Come on, there you go. So reminder, Leibniz notation was dy over dx. For the second derivative, it's going to be d squared y over dx squared. That first, those look like z's. Let me write the little curvy 2's. There we go. And yes, I put the 2's in the right spot. I could explain why, but I don't know if anyone would care. Essentially, when we take the derivative in Leibniz notation, it's written as d over dx. So essentially, when we take the derivative of dy dx, it's just the d's that group together. So we have d squared y over dx all squared. If you were curious as to why the 2's are in the spots that they are. But we don't use Leibniz notation that much that you'll probably remember that. So let me erase this kind of side note. That was a reminder of how our Leibniz notation went. So at this point, what we're going to do now is we're going to remind ourselves of stuff that we already knew. And oh man, I forgot to, dang it. Forgot to fix the notes and put them back up. One of these in each case should be a less than instead of a greater than. I gotta fix that. I'll fix that later today and put up new blank notes just in case. Not that I think anyone would go back and get the new blank notes, but just in case. So sorry, those should have a greater than and a less than, both in each case. So part of this we already know, and then we're essentially going to build on it. So remember back from 2-2, and I circled it about 5 million times, and I told you that it was going to be really, really important, and I meant it. So remember, if the derivative is positive on an interval, that meant that your original function was increasing. And if your derivative was negative on an interval, come on, catch up. If the derivative is positive, the original is increasing, and if the derivative was negative, the original is decreasing. Come on. Here we go. So now, well, what about if we think about if the second derivative is positive? So if you think about it in this kind of first thing, we have the first derivative, and then we kind of go backwards to the original function. Well, if I have the second derivative, if I wanted to use this kind of same relationship, I would have to, whoops, zoom back out. I would essentially have to go backwards, if you will, to just regular f prime once it catches up. But if we kind of follow that pattern, if you will, if the second derivative is positive, then the first derivative is increasing. It's like the same idea as the thing above it, just with a new derivative now. And if the second derivative is negative, then the original derivative, the first derivative, must be decreasing on that interval. So we kind of took this idea that we had already and kind of now have mirrored it with this new derivative that we're going to talk about. Once this catches up to me. I really don't know if yours are lagging as much as mine, but just in case they are, I will wait. There we go. Decreasing. So same idea, just kind of mirrored for this new derivative that we have to talk about. So, let me leave that part in, but scroll down a little bit. So if the derivative is increasing, scroll down. There we go. So if f prime is increasing, then the slope of the original function is increasing, because remember the derivative is a slope. So that means it's going to end up bending upwards. And if f prime is decreasing, then the slope is decreasing, so it's going to be bending downwards. So if you think back a couple sections ago, back in chapter 1, we had some definitions for something that meant that the function was bending upwards or bending downwards. And it ended up being the concavity of it. Concave up, concave down. Remember these doodads? Concave up, concave down. They're coming back. So essentially, if the second derivative is positive in an interval, the original function f is concave up on that interval. So before, we kind of just had to look at whether it bends upwards or downwards, and at this point we still have to do that a little bit, still really by sight. But eventually we'll get to things where we don't have to use our eyes and we can use algebra and calculus. So if the second derivative is negative, then the original function is going to be concave down. So now we kind of have these relationships not only between f and f prime, but between f prime and f double prime, and now between f and f double prime. So we've got a lot of relationships going on. So a lot of times we'll see it kind of summarized in this table. I very highly suggest you just memorize it in terms of this table. I'm not kidding. We use it so often. And I think writing it down in a table like this is kind of the easiest way to remember it. Now, you kind of have to remember the first one, just kind of off. You have to remember one piece of information, and then the other ones you can hopefully kind of draw out from it. So you might need to remember that if the original is increasing and the derivative is positive. We don't know anything about the second derivative yet. Can't say anything about the second derivative just from the fact that f is increasing. And then if f is decreasing, f prime is negative. So all of this is just essentially summarizing all of the things that we said above, just in a kind of nicer format. Now, the next thing we saw was essentially that this relationship kind of also holds for like the step over, if you will. So if the derivative is increasing, then the second derivative is positive. And if the if the first derivative is decreasing, then the second derivative is negative. That kind of pattern just kind of shifts itself over. And then we're also told kind of this new relationship between the original function and the second derivative. So if the second derivative is positive, the original is concave up. And then if the second derivative is negative, it's concave down. I cannot stress enough how much you'll need to have the ideas of this table in your brain. It is used so often, not only in this section in chapter 2, but it also comes back, the ideas come back in chapter 4, and it just keeps coming up. So really, I'm not kidding. Know those relationships backwards, forwards, sideways. Eat them, sleep them, drink them, live them, I don't know. Anyway. So visualizing concavity. Again, we kind of talked about it before, but let me remind you, we kind of have these two pieces of it. And now let me kind of add in kind of the new notation we have once this catches up to me. Can I scroll down a little more? There we go. So this whole thing is concave up, which would mean that the first derivative is positive. Nope, first derivative is increasing, sorry. So that's for the entire kind of piece of that. That's why I kind of wrote it on both sides of that line. But then when we split these up, we essentially have two options. We either have that the function is decreasing, which means that the derivative would be negative, or we have that the original is increasing, and therefore the derivative would be positive. And then we've got our concave down option. If it's concave down, that means that the derivative is decreasing in both cases. Decreasing, come on, there you go. And then again, we kind of have these two choices. Either the original is increasing, so the derivative is positive, or the original is decreasing, so the derivative is negative. So once that catches up to me, there we go. I'll leave this up for a couple more seconds so y'all can catch up. We'll do a couple of examples. We might actually finish 2-4. I really meant it when I said that 2-4 is short. It's really short. We might finish it. Anyway. Questions, concerns so far? We haven't really done any examples. We've just been writing down information, but. Okie dokie. So, example. For the given graphs, determine whether when their second derivative is positive, and when it is, I don't know why I say they are. I guess because I'm referring to multiple graphs? I don't know. Anyway. And when the second derivative is negative. Essentially, when is the second derivative positive, when is it negative for these graphs? So looking at part A, well, is that concave up, concave down, or maybe a little bit of both? This one is going to end up being purely concave up. Essentially because it looks like, when we kind of look at concave up and concave down, catch up to me. Come on, you can do it. I believe in you. Here we go. When we have our like kind of concave up and concave down pieces, this graph looks kind of exactly like the concave up piece. So let me kind of split these up. Since this is concave up everywhere, now this function was named f, so we would have f double prime of x is greater than 0 everywhere. If I wanted to say from negative infinity to infinity, I totally could, but just saying that it is positive everywhere would also get that point across. Now, if I look at the second one, I want to know whether that's concave up or concave down. Once this catches up to me. Come on, you can do it, computer. I believe in you. So essentially, if we look at this, that doesn't look anything like the thing on the left. But the thing on the right, if I split that up into its pieces again, this kind of leftmost piece resembles that graph. The lag is so real. Come on now. You got this. You can do it. If your screen is keeping up with how I'm actually writing, then I probably sound like a lunatic. But both of my screens are lagging super hard, so I just want to be careful. There we go. So kind of that leftmost piece of the concave down one does look like the graph that we have here. So essentially that entire graph would be considered concave down. So this would be concave down everywhere. Now this function's name was g, so we would say g double prime of x is less than 0 everywhere. And again, if you wanted to say negative infinity to infinity, that's perfectly fine, as long as it gets the point across that it's everywhere. All right. Let me redraw my concave up, concave down options again. Let it lag for 5 million years. Oh, hey, that caught up pretty quickly. So for part C, we have this next graph. It actually is going to be a little bit of both. Because if we split it up right here, if I look at kind of this little first piece, well, that's going to resemble kind of that left piece again of the concave down option. Once this catches up to me, you'll know what I meant. Go. Maybe we won't finish because the lag is so real. You got it. Come on. Catch up to me, please. There we go. So kind of that left side of the graph matches kind of that left side of the concave down option. So the name of this function is h. So we'd have h double prime of x is less than 0. And let me actually use function interval notation here. Now we don't have numbers on this graph, but that's going to split at 0. It splits when it crosses that x-axis at the origin. So we can essentially say that the second derivative is negative because that piece is concave down. Maybe I haven't been stressing that enough. So that piece is concave down, so it's going to be concave down from negative infinity to 0. And just like with increasing and decreasing, you kind of get to choose whether or not you want a bracket or a parenthesis on that number 0. I'm just going to choose a bracket just because I feel like using a bracket today, I guess. But so our second derivative in that kind of first half of the graph, if you will, is going to be negative because it looks concave down. And then if we look at the rest of it, and we look at our concave pieces, well, which piece does that most likely resemble? Well, if we look at, it doesn't look anything like the concave down options, but if we look at kind of the rightmost side of the concave up option, the graph, most closely resembles that piece. Catch up to me. There we go. So it might not look perfectly like the concave up and concave down options, it just has to kind of resemble it. So that means that since in that piece we're concave up, the second derivative would be positive. So concave up, positive, concave down, negative in terms of the second derivative. So we would say that this is positive on 0 to infinity. Let me kind of clean this up a little bit and kind of erase these concavity options, except for this one until I triple check any questions, concerns on that example. So again, at this point in time, we're still pretty focused on just having to do it visually, but we'll eventually have some ways to not have to do that visually as well. 3 minutes. I don't think 3 minutes is enough to do this last example in the amount of time that I want to. Like, I could rush it, but I don't want to rush it. So I'm going to save this last example. We almost got done 2-4, but we had one more example that we'll go over on Wednesday. Give me 2 seconds to think about what I want to put on your quiz, and then I'll tell you. What do I want to put on your quiz? Let's see. Let's make it... Quiz on Wednesday. I wanted to cover part of 2.2, so that would be choosing the correct derivative graph. I'm only going to go that direction, give you the original, ask you to find the derivative graph. So that's from 2.2, and then 2.3. We're not going to cover 2.4 since we just got into it. But 2.3, so I might ask you to interpret a derivative value, and also kind of what we did today where we estimate values of a function given essentially f of x and f prime of x. That I deal with those Kenyan shillings where we had to find f of 6 and f of 10. That I do. So 2.2 and 2.3 for your quiz on Wednesday. So it'll be a multiple choice. Maybe 1 or 2 multiple choice for the choose the correct derivative graph. And then I'll ask you to interpret a derivative value and estimate values of a function given f of x and f prime of x. Well, that doesn't sound good, Benji.